Let's talk more about proprioception, because this is one of the most complicated aspects of haptic perception. It means parts of your body that belong to your own self and understanding their motion in the world. So can you get a sense of where your hand is in space and how it's moving without looking at it? So this is really important. If you want to put a hat on your head, you can't see where your arm is. If you're moving your hand around in the dark to turn off your alarm clock in the morning, that's another situation where you're relying on your proprioception, not vision, in order to know where your limbs are in space. In much of the literature, proprioception is defined as the perception of your body in space, but it can also mean forces that, in terms of interaction with the environment. However, people usually think of interaction with the environment as exteroperception, so proprio being self and extero being external to oneself. Just putting a definition that we use in this class because different people will use proprioception in different ways. One of the interesting things about proprioception is how its capabilities are distributed over the body. Here's a representation of a human arm and various joints that are on the arm. So for example, the PIP joint on the finger, the MCP joint also on the finger, wrist, elbow, shoulder, and two locations on the shoulder. And at all these different locations, you have a certain capability to measure how much an angle of your arm changes at that joint. This term up here, which is just noticeable difference, basically gives you the threshold of how much you have to move before you would notice that your arm has moved at all. And one of the things you might think about is where on the body would have the smallest, that is the highest resolution of proprioception. How much would they have the smallest just noticeable difference? Because a small just noticeable difference means a very high sensing resolution. So now I'm going to give the answers to that over here in this last column. So if you look at these different joints, you'll see that you have, depending on which paper you read, some range in the 2.5 to 6.8 degrees way out here at the fingertip. And yet the shoulder has much better sensing resolution, almost an order of magnitude better. You might think about why that's the case. Why would it be important to have better sensing resolution here than way out here? Because you think a lot of interesting dexterous manipulation happens at the hand. Well, one reason is that when you have a change in your shoulder angle, there's a long lever arm out to your hand. And so very small changes in your shoulder angle will result in large movements of the hand. So if you want to know where your hand is in space, it's actually more important to have accurate sensing of the joints that are closer to the trunk than way out on the end. The other reason is that if you're trying to do some sort of fine manipulation task, it's really not just proprioception that you're using. Of course, you're using your tactile sensing capability, and you have great resolution of mechanoreceptors on the glabrous skin of the hand, and that will make up most of the time for having poorer proprioception in that location of the body. The story is a little bit more complicated than that, though. This is a chart that was developed by Lynette Jones from various experiments that show how this movement detection threshold, or this just noticeable difference, will change for these different joints, elbow or index finger, depending on both how fast you move and whether your muscles are contracted or relaxed. And so your ability to sense movement and position is not static, it's depending on how you're moving. So this is one of the things that makes human haptics complicated, is that the context of the movement and what the configuration of your body is can be very important in determining what you sense. Luckily, as humans, we have a lot of experience of just moving around in the environment and learning to interpret that information. But whenever we have to learn a new task, like playing tennis or a child learning how to walk, you're having to adjust your model for what kind of proprioceptive feedback you get back and what that means in terms of your movement in the world.